Hey everybody, my name is Brazill, and today I want to go over a rational function problem and how to solve it. Okay, so first, let's discuss what a rational function is. A rational function is a function that contains both polynomials in the numerator and in the denominator. It also has to contain rational numbers in the coefficient, as I have drawn here. The reason it's called rational is because it contains one polynomial being divided by another polynomial. A rational function has to be in the form of f of x equals px over qx, where px and qx are both polynomials, and qx cannot equal 0. The problem that I'm going to be solving today states, describe the key characteristics of the graphs of rational functions of the form f at x equals ax plus b divided by cx plus d. Explain how you can determine these characteristics using the equations of the functions. In what ways are the graphs of all the functions in this family alike? In what ways are they different? Use examples in your comparison. Going back through this question, let's analyze the important parts of it. First, the question asks to describe the key characteristics of the graphs of rational functions in the form f at x equals ax plus b divided by cx plus d. The important parts in this section is characteristics of graphs of rational functions. This basically sets up the whole question and deals with importance of rational functions, which we studied a lot in Unit 3. Part A of this question states, explain how you can determine these characteristics using the equation of the functions. The important part in this question is using the function to help with answering the question. Part B states, in what ways are the graphs of all the functions in this family alike? The importance in this part is finding similarities between each rational function. Part C states, in what ways are they different? Use examples in comparison. This part deals with differences between rational functions and is basically the opposite of Part B, which is finding similarities. In this video, I want to talk a lot about vertical and horizontal asymptotes. I would like to talk about what they are and how they apply to the function given in all rational functions. I also want to discuss x and y intercepts and how they apply to the function given in the question and how they compare as a whole to rational functions. Okay, so determining the characteristics of this function, we'll have to dissect each part of the function. So rational functions contain horizontal and vertical asymptotes. An asymptote is a virtual line that prevents a function from extending past a particular point. The function continues to infinity without actually touching that virtual line. In essence, it continues to get smaller and smaller all the way to infinity. A horizontal asymptote is that virtual line that intersects the y-axis at a certain point and is perpendicular to the x-axis. A vertical asymptote is that virtual line that crosses the x-axis at a certain point and is perpendicular to the y-axis. Now, knowing what vertical and horizontal asymptotes are, we can now apply this to the function that we were given. We can determine the horizontal asymptote through the value a divided by c. There are three types of horizontal asymptotes. One where the a value is greater than the c value, one where the a value is smaller than the c value, and an oblique asymptote where the degree of the x value in the numerator is greater than the degree of the x value in the denominator. For our vertical asymptote, we can determine by factoring cx plus d, which will become negative d over c. Asymptotes are huge characteristics in a rational function. It becomes very useful when graphing because it allows for you to easily determine roughly what the function will look like. For example, if we make up a function like f at x equals 8x minus 2 divided by 4x plus 3, we can apply what we just learned so it becomes more clear. Comparing f at x equals ax plus b divided by cx plus d to f at x equals ax minus 2 divided by 4x plus 3, using the information that we just learned, our horizontal asymptote is a over c and our vertical asymptote is negative d over c. In this case, our horizontal asymptote would be 8 divided by 4, which if we simplify is 2, and our vertical asymptote would be negative 3 divided by 4. Another key characteristics of rational functions are x and y intercepts. They are the points in which the function crosses the x and y axis. First, we can determine the x-intercept through the value negative b divided by a. We know this because the y value is always 0 at the x-intercept, so we make the function equal to 0, multiply the denominator by 0, and we're left with 0. And finally, isolate by x by subtracting both sides by b and dividing both sides by a. For our y-intercept, we can determine the value b divided by d. We know this because our x value is always 0 at the y-intercept, so we plug in 0 for x, a multiplied by 0 is 0, c multiplied by 0 is 0, so we're left with b divided by d. Now, to talk about how all the graphs of this function in this family are alike, all rational functions in this family have to contain vertical and horizontal asymptotes. If you were to graph every function in this family, it is certain that every single one of them would contain vertical and horizontal asymptotes. The value for those asymptotes might be different, but it is certain that they will contain them. For example, one function could be f at x equals 4x minus 6 divided by 4x minus 3, with a vertical asymptote at 3 divided by 4 and a horizontal asymptote at 4 divided by 4 when simplified is 1, and another function f at x equals 6x plus 3 divided by 2x plus 7. The vertical asymptote would be negative 7 divided by 2, and a horizontal asymptote at 3. Just because the values for both the vertical and horizontal asymptote are different, it is for sure that both of these functions contain them. There are rare cases in which a rational function does not contain asymptotes. An example of this case is a function like f at x equals 2x plus 1 divided by 2x plus 1. This function will be a linear line with the pinhole at negative 1 divided by 2. Now, to talk about how the functions in this family are different. Not all functions in this family have to contain x and y intercepts. X and y intercepts are unique to some functions, but are not in all the functions. Some functions cross both the x and y axis, some cross only the x and not the y axis, some cross the y axis and not the x axis, and some cross neither. An example of a function that crosses both the x and y intercept is f at x equals 2x divided by 2x minus 8. For this function, the x and y intercept is at the origin 0 and 0. An example of a function that crosses the y-axis and not the x-axis is f at x equals 1 divided by x minus 3, where the y-intercept is at 0 and negative 1 over 3. An example of a function that only crosses the x-axis and not the y-axis is f at x equals 1 divided by x plus 3, where the x-intercept is at negative 1 over 3, 0. An example of a function that crosses neither the x-axis nor the y-axis is f at x equals 1 divided by x. Rational functions can be used in the real world. Unfortunately, it is not as common as it could be. It requires a more specific skill in a certain situation for it to come up. Professions such as engineers, biologists, chemists, or physicists are professions that rational functions might come up. Physicists would use rational functions when modeling a gravitational field or magnetic field. In evolutionary biology, it would be used to model predator-prey interactions. In chemistry, it can be used for enzyme kinetics. In engineering, it could be used to develop and improve aerodynamics.